These are the notes for Chapter 22 in the McGraw-Hill book on it's organic chemistry, the V2 or Chapter 2. So move on, and we'll help you if you have the PowerPoint in front of you. You probably can't see as well up here, but you can kind of see what page we're on. So we're going to start out by adding a couple of things on to what we talked about last chapter. Last chapter, we've got a kind of an introduction to organic chemistry and learn how to name a lot of the organic compounds. We talked about double bonded compounds being alkenes, but there's also some arenes or the ring compounds, aromatic compounds. We did not talk about the aliphatic compounds that have more than one double bond. So we're going to hit that real quick. And if you have a compound, let's say that we had pentene, but it has two double bonds instead of one. So we have 1, 2, 3, 4, 5. First thing you do, pent. And remember, we always try to focus on the parent chain first. Well, we're going to start with one with double bond. So that would be pentene, but remember we've got to tell people where the double bond is. In this case, this double bond is on the first carbon. Remember, we count from the end closest to the double bond, so that would be 1 pentene. Well, if we had a second double bond, wherever it might be, let's say that it's on this second carbon, for instance. Now we've got to get rid of 2 hydrogens because you can only have 4 sticks coming out of any one carbon. And actually got to get rid of that one. So we got 1, 2, 3, 4 out of that carbon, all involved with double bonds. Well, we're going to call this 1, 2 pentene. So we've got 2 of the double bonds instead of 1. So just remember that you always have to start with the parent chain, and you know that you've got 2 double bonds here. You have to tell people where they are. So often you'll see this as 1, 2 pentadiene. They use the di to tell you that it has 2 double bonds. So that's probably the best and most accepted way to do that. So remember, look at the parent chain. Name that first. If it's got a couple of double bonds, you just do what we just said in order to tell people about that. The other thing is that we talked about benzene rings. Well, we're going to add on another type of ring, very common, probably one of the most common benzene rings would be the toluene. And toluene is basically a benzene ring with a methyl group on top. So it's so common that instead of just saying methylbenzene, they call it toluene. So this is our toluene molecule. If we had something else on it, like let's say we had a bromine over here, well, then we're going to call that 2 bromine, 2 bromo toluene. And we always use the methyl group as the anchor for where the 1 is. So if it were down here, it would be 1, 2, 3. If it were all the way across, 1, 2, 3, 4, and beyond that, if it comes around this other side, then we start counting the other way, 1, 2, 3. So I just wanted to make sure that we introduced toluene so that you knew that. So we're going to move on with Chapter 22 stuff. And in Chapter 22, we're going to introduce some of the substituent groups. In other words, it's kind of like accessories for your car. We're going to buy some more accessories here and add a radio and maybe tinted windows and some things like that. So the accessories, the extra things that make the car behave differently, that's what these groups are. So we're going to start, of course, we already talked about halocarbons in the last chapter, and the halocarbons are the compounds that have halogens from group 7A. And remember that if we have chlorine, then where it is, we call it a chloro group. If we have bromine, it's a bromo group, iodine, iodo. And it's basically just the same stuff that we talked about. Just a reminder that, when we have a halide as a functional group, that instead of chlorine, you drop the INE and you put an O. The chart on page 787, that would be well worth your while to make a copy of that. I have copies available in the classroom. Use that as your main study guide for this chapter. I would say anywhere from 60 to 70% of the questions could be tracked directly back to looking at this chart and learning the types of groups and the way we name them. Make sure you know what each functional group is and then what the compounds are called that have those functional groups. So this is a picture of that chart. Chart, like I said, is available in the classroom. There's also one in your book. We're going to start, again, they have halides as the first thing, even though we've already talked about that in the last chapter. They wanted to make sure you understand it's not always just carbon groups, so that's why they introduced those early. So if we have a chlorine on, say, the third carbon on a hexene molecule, then you would say 3-chloro, 1-hexene. And you tell people where the groups are. It's kind of like telling somebody where a friend lives. You give the address and somebody says, oh, well, I can find that. I'll plug it into my GPS and find it. So remember that on the rings, the benzene rings, that if we have chlorine, then we say it's chlorobenzene. If we have bromine, it's bromobenzene. What if we have two? Well, if we have two, then wherever they are, and I'm going to start up the top. Let's say there's one chlorine sticking out on the top, and there's one on the next carbon. That would be 1,2-dichlorobenzene. 1,3-dichlorobenzene and 1,4-dichlorobenzene. We also have other names for those from the Greek terms that we have we have ortho, which means close or next, and then we have meta, which means middle, and we have para, which means away or alone. And if you wanted to call this one para-dichlorobenzene, that's perfectly acceptable too. So those are things from last chapter. We're just kind of hitting them again, make sure that you're up to speed with those. There's two main groups of halides. We have the alkyl halides, which are the aliphatic compounds. Remember, aliphatic are the ones that are stretched out, it's kind of a zigzag chain. Aryl halides are those that involve the benzene rings. And we've already kind of gone over that. Here you've got the ortho, meta, and para dichlorobenzenes. So we're going to talk about boiling points and properties. Obviously, in this top graph, you can see that when we start with one carbon, that's minus 162 degrees boiling point. That would be something like methane. When we turn on this spigot and let methane out, methane's got hydrogens all the way around, and it doesn't like the other methanes. Hydrogens aren't attracted to hydrogens, except for the van der Waals dispersion forces. So dispersion forces, remember, are where there's electrons moving inside. Wherever there's electrons moving, there's a magnetic field around it, and a very slight magnetic attraction. When those molecules hit a methane, they bounce off, and they go out to the walls and become a gas. If we cool it to minus 162 degrees Celsius, then when they hit, they're moving so slow they stick together. Kind of like throwing a magnet at a metal object real hard, hits and it bounces off. But if you move it over there slowly and touch it, it sticks. And when it sticks, that means it's a liquid, and if it sticks even more, it becomes a solid. So you can see real easily here that it's somewhat linear when we go from minus 162 all the way up to about 142 for 8 carbons, which would be octane. That would be like kind of the mid-range of what is in gasoline. and that corresponds to the boiling point of gasoline. Not that we want to boil gasoline. That's not something I would enjoy doing unless I was paid a whole lot and had a fireproof suit on. So over here we see the melting points not quite so linear down on the bottom. As a matter of fact, they're very close, like methane, very close to boiling and melting points. We can actually make methane solid if we get the right pressure and the right temperature. And we look at methane over here, then we go to ethane and back down to propane. Propane actually is just a tad lower in melting point, so there's a little bit of nonlinearity down there on the bottom, but as we go up you can see that the bigger it gets, the more energy to melt it. And that's like anything else. Think of tearing a house down. Tear down a dog house, boom, 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 load it up and take it out and it's done. Take down a 3-story home and that takes a lot more energy because it's a lot bigger structure. The bigger they are, the harder they fall. So keep in mind, bigger molecules, higher boiling point. There will be questions on the test where I ask you which of these molecules would you think has a higher boiling point. Well, number one thing, look at the bigger ones. The bigger they are, the higher the boiling point. And melting points somewhat the same. And I wouldn't give you propane and ethane because they're kind of opposite, but we've talked about it, so you should know that. All right, so as far as that goes. Now, what if we add a halogen? Well, if you add a halogen, some of the halogens are fairly heavy. I mean, chlorine, bromine, iodine. Iodine's 126.9. That's a pretty heavy molecule. When you add that, it's kind of the same thing. The heavier and bigger something is, the more energy it is in order to turn it into a gas, because we've got to drive that stuff up and away from its partner. And so keep in mind that if you had an iodide compound, it would have a boiling point in melting point higher than the fluoro and chloro compounds in almost every case. There's probably exceptions, there always are. I can't think of one right now. So keep that in mind. Size, number of carbons, which also corresponds to heavier, and then molecular mass. The heavier the molecular mass in general, the higher the boiling point. So there are 4 main forces that cause things to boil high or low. And these are all intermolecular. In other words, here's a molecule, here's a molecule. Not the intramolecular, which would be the covalent bonds, but inter, like international, between 2 nations, between 2 molecules. There are 4 ionic compounds. Actually, it is a bond, but it's also an intermolecular attraction. So it's kind of both things at once. And those are the strongest. You try to melt salt or any of the salts, you got to have a real heavy-duty burner, and you got to heat it to a high temperature. That's because they have such good bonding. It's like trying to, little piggy trying to blow down the brick building, okay? Not going to happen. Or the wolf. I guess the piggy wouldn't want to blow down his own house. So the wolf can huff and puff. He's not going to get that brick building down. Other things like hydrogen bonding, pretty strong too. That might be like the wooden house. Okay, a little bit weaker, but still pretty strong. Water has a high boiling point. You think about boiling points, think, well, 100's not that high. It is high for a small compound like water. Water has a molecular mass of 18. Methane has a very comparable molecular mass, but it boils at -162. So, that's the temperature you'd expect water to boil at. And if it did, we wouldn't be here because we're mostly water. So, the thing is, what is it that makes water boil so high? Hydrogen bonding. It sticks together. The waters stick to each other. We heat it up, they still stick, and they start vibrating. We heat it up, we get it up to 100 degrees, and poof, there it goes. It's a gas. So the intermolecular attractions are what cause that. When we step up to the next thing, and related to hydrogen bonding is dipole-dipole, which would be plus-minus attractions. That's what hydrogen bonding is. It just happens to be a real strong dipole-dipole. So if molecules have plus-minus attraction, then they might have a fairly good boiling point too, maybe somewhere in the range of 0 to 100. The final one, what about methane? Why does it even stick together? Well, if we get it cold enough, minus 162 Celsius, and it hits another methane, it'll actually stick together and condense and form a liquid because of the van der Waals forces. That's a generic term called dispersion forces. The moving electrons make it have a slight magnetic field, kind of like tossing a weak magnet up on the board. You know, if you toss it light enough, it might stick. If you throw it hard, it bounces off. You gotta take the energy out of it by cooling it down when it's a gas, and you can make it turn into a liquid. So very important points. Boiling point increase as the number of carbons increase. Boiling point increases with the molecular mass increase. Almost always a rule. Any questions I give you are going to follow that rule. I'm not going to throw an exception in there on the test unless we make a real point about it. Also, branching decreases boiling point. So let's say we have different isomers of pentane. Pentane has 1, 2, 3, 4, 5 in a kind of zigzag line. What about if we take one of those off and stick it in the middle and make a branch? That would be, say, 2-methyl propane or butane. What if we take one more off and stick it into where we've got a cross shape molecule, which would be 2,2-dimethyl propane. Now we've got a 3-carbon chain. Well, that's very branched, and by branching it, we've decreased the boiling point. So it makes it not have so much attraction to the other molecules. It kind of keeps the other molecules at distance so that they don't, the van der Waals dispersion forces can't grab onto each other. So branching, so on the test, if I give you a straight chain with 5 carbons, a single branch with 5 carbons, and a very branched compound with 5 carbons, to say which has the lowest boiling point, well, the branched one would have the lowest boiling points. So we're going to move on, talk about substitution reactions. In this chapter, we're going to have substitution, addition, dehydrogenation, hydrogenation reactions. So we're going to do all those in a later day. Today, we're only doing substitution reactions. And I'm either going to use halides or I'm going to use XX, which can stand for halides or can stand for other molecules. Another one that you may see on the test would be water as a molecule that does the substitution where the OH and a H swap places. And you'll end up with a molecule that has an OH, we're going to find out is an alcohol, and H2. So what is substitution? Well, we're going to take an organic molecule and some molecule, either HOH or Cl2 or Br2, and we're going to introduce those in the same container and either put enzymes, catalysts, or heat that's going to make the reaction go, and one of the, in this case, one of the Cls will kick out a hydrogen and take its place. That's substituting or substitution. We end up with, in this case, HCl and chloromethane. In other words, it's a methane with one Cl and, where a H used to be. Substitution. Okay. Look at the reaction. There's several others in the chapter. Start working on your review. We have a lab where we're going to put these molecules together, and I think that'll help you see what they look like. Study hard. Good luck, and we will see you on the next video.